few hours source of energy.
Oh, Lord.
You've done the basics. They are
What the heck happened there?
direction notes where people there's nothing left. Just really, it's just that Scott answered as a nice. So what I'm setting is how to so that it remains useful. There are many people. But yes, this is definitely my recommendation. So you just started. Is this?
Well, yeah, it's been almost 2 months now.
You happy with that?
Yeah, I think so.
Okay, thanks everybody for making it back from lunch. So we're gonna pick up where we left off. I guess if you're still looking to work along, you can bring Pluto back. And we'll probably go with this for about an hour, and then Stefan is gonna come down and start on the Clifford simulation. So I guess stick around for that if you're interested, and that'll be probably the rest of the day. And then there's quite a few exercises here, so I'll try and I guess like give people a little bit of time to get started on each one, and you're welcome to keep working on it on your own if it interests you, and chat about it later. So just I guess summary from before lunch when we were all probably pretty hungry and like not thinking. So we went from a pretty simple method of doing circuit simulation for state vectors, just using like the fully constructed unitary for a specific gate, and then use reshape, permute, reshape to make it a bit faster, and then the bit shifting approach to get substantially better performance, first for a single qubit gate, and then for a gate on 2 qubits. So we're going to keep extending that to other situations, looking, for example, at like controlled gates. We're going to look at how we can compute expectation values using the same bit shifting formalism, look at how we can efficiently sample. For example, if we're doing a quantum circuit simulation where we have finite shots. And then time permitting, we'll talk about how we can extend most of these same functions to handle density matrices, Kraus noise, and mixed state simulation. So cool. So the first thing we'll pick up with is controlled gates. So the classic example is C0 or CX. So these controlled gates do nothing if the controlled qubit is 0, and they apply a gate if the controlled qubit is 1. So a matrix representation of one of these might, for example, be this C0 here. I can also try and use the board a little bit more. But effectively, this maps 0, 0 to 0, 0, 0, 1 to 0, 1, 1, 0 to 1, 1, and 1, 1 to 1, 0. So there are couple options for how we could do this. We could just apply it as a naive 2-qubit gate, but we can actually save ourselves some effort and make things more efficient by recognizing the fact that this thing is controlled. So it's effectively block diagonal on the first 2 elements up here. So in this controlled case, only states with the 1 state on the controlled qubit have anything changed. The others are completely untouched. So if we target those states only, using this expand int and flip bit functionality we developed earlier, then we can actually cut the amount of iterations we have to do in half, which is pretty great. So here again is a simple example of how we can do this, where I've got my psi, my input gate. So in this case, it would be like C0 or something, the target qubit and the control qubit. And here I go through and expand twice. This is also, I guess, kind of a hint if you got stuck on the previous exercise for 2-qubit gates. Then from there, you can use the flipping to target the specific sector where for the control qubit, everything is in the up state or the 1 state. And then this effectively becomes a single qubit gate application. So this is just another, I guess, relatively simple example of how we can use the bit shifting, but in a more specialized way where we save ourselves a bunch of effort, not targeting states that are really not affected very much by the gate. So one, I guess, small trick here is that I actually only passed in the non-controlled segment of the gate. That's like kind of an arbitrary choice that you could decide to do. And then the exercise here, just to get started, is relatively simple based on the existing function. So this is controlled on the qubit, but the controlled qubit being in the 1 state. And of course, you can have a negatively controlled gate as well, where it's sort of the reverse of this, where instead of things only happening if a control qubit is in 1, they only happen if it's in 0. So if you want, you can try and extend this to make like a apply neg controlled gate. It's very, very similar if you want to try and do that. It's actually fewer lines rather than the same amount. And if you want to keep going, you can even try handling gates where there's multiple control qubits. So an example would be like CC naught. So there's two controls, or you can have a mix of controlled and negatively controlled qubits. So I'll give people, I guess, like a few minutes just to try that / finish setting up their Plutos. Yeah.
How do you run the whole Pluto?
If you just hit Shift Enter, it should try and run everything. Or there's this button on the top right that says Save All Changes. Every time you save, that also runs everything to make sure that the notebook is still valid. So,
Like I close my.
sorry?
Min-max function.
Oh yeah, min-max. It's effectively sorting these two integers, like which is the smallest, which is the biggest.
First.
Yeah.
For the open controlled case that you
Yeah, the negatively controlled case is actually easier because there's one fewer flip you got to do. I'm like overheating. Okay. So once we have support for things that are controlled, we basically have every kind of gate that we're going to need to do like almost every quantum circuit. Again, we're just looking at pure states for now, so not worrying about noise. And then we can move on for how we could apply this to compute expectation values. Another pretty essential thing we're going to want to do just to understand sort of what the mean result we should get if we do like an infinite number of shots on some quantum circuit. So here we already have a lot of the infrastructure built up, since we know, again, that the expectation value of O is just the inner product of it with respect to psi, and we already have a bunch of the hardware we need for computing sort of the right 2/3 of this equation. So we can effectively port over a large fraction of the code. And again, we're going to look specifically at the single qubit case here. For now, we'll just look at a single qubit observable, but of course you could have more qubits. And if we want to take advantage of threading, we need to be a little bit careful because effectively what we want to do is compute, given whatever O is, all of the individual inner products here and then sum them up. So effectively we're doing a giant map reduce. But when we do the sum, we need to be careful that we don't end up with some sort of race condition if we're using threading. So who here has used like OpenMP before? Or like Julia threads? By some people, basically the same people. So the risk that you run, I guess, oh, this is a good opportunity to use the markers. Actually, I'll just ask, who here knows what a race condition is? Okay, some people. So the risk that you run, if you're not careful, so if you're me and you're not careful, is you have thread 1, let's say, and thread 2. I already break this marker. So this gets sort of like result 1 for his piece of work. This one gets result 2. And there's some final result that's going to be the sum of these for every single chunk of work. The risk is that, let's see the total. Sorry, again, my handwriting is not so great. The risk that we run with the race condition is if these are running in parallel, that this one fetches this and then tries to add itself to it. And this one simultaneously does the same thing. So that it effectively ends up overwriting the result of this without accumulating result 1. So the result of 1 is just completely gone because the two of them are racing to deliver information to the final result. So there's a bunch of different techniques you can use to work around this. One of them is to use what are called atomic operations, which effectively says, okay, only one thread at a time is allowed to access this chunk. So that means effectively the threads have to form a little bit of a queue where they say, okay, thread 1 has sole access to total result. It adds its result in, and then it hands over control to thread 2. It adds its result. So that's definitely one option you can use. You can end up with some slowdowns there because there's only one result. And so if you're not careful, you can end up with a bunch of threads sort of stuck waiting in the queue for exclusive access to the result. Another option, which I implemented here in the sample function, is that each thread can accumulate their own results, which is safe for them to do because they have exclusive access to their element of the array where they're accumulating. And then at the end, we can sum up the total number of temporary results, which can work reasonably well if the number of threads isn't gigantic, which in most cases it is not. So those are two different sort of techniques you can use if you want to try and avoid these race conditions. These are a really common source of bugs in parallel applications where you have something that updates and then another thing updates based on the previous version and just discards the work you already did. So it's worth, if you're interested, looking into how the atomic operations, which Julia has really good support for, actually work under the hood. And we might see more of that later, for example, if we do the GPU stuff. But yeah.
Second method that you mentioned is in this example.
Yeah. Yeah, so here we create this temporary results array that's all zeros and it's of length the number of threads. And then when we're actually doing the dot product, each element, so each index using the bit shifting approach we showed earlier computes one portion of the final dot product for that specific amplitude. And then it writes that specific result into a thread exclusive region in the temporary results array. And then once all the threads are done, so outside of the threaded block down here, we just sum up all the temporaries. And this works because it avoids having different threads right on top of each other. So another way you could do this if you wanted to is you could instead just have this be temp results. You could just have it be like result equals 0.0, let's say. And then down here, instead of this, you would have like threads.atomic add to, like result something. I don't have the exact syntax off the top of my head, but that would also be a reasonable way to do this. And it would also be a good case for benchmarking it and seeing in your specific case which one runs faster. I only showed one of them just because I don't know, I kind of like this one, but there's really a priori what it kind of works. And you can test this for correctness also with your initial naive approach above. So I ran a couple of these and they came out looking correct, but in of course the real world, you would probably want to test this in a more thorough way. So the other thing you can see is there's like a little bit of type difference here because I already know that since this is a Hermitian observable, the output has to be real. Julia in the just naive dot product case does not know this, so it outputs a complex number. And we can also again check this for another operator. In this case, I did X. And then finally, with some benchmarking, since I am a goofball, I switched the order of these, so I'll switch them back. With the bit shifting as compared to the naive one for a 12-qubit circuit, you can see that, again, there's like a 4 order of magnitude improvement, which is, again, maybe not that surprising because I already mentioned that the naive version is like incredibly bad. But it does show that if you're willing to spend a little bit of time, I guess, there's some improvements to be gained. The other thing that's also notable with the naive one is it does spend a lot of time in the garbage collector because it's allocating so many matrices, whereas the shifting one does not have very many allocations, and I think most of those are just tasks. So, hooray! Okay. So the next thing I wanted to talk about is doing categorical sampling. So of course, like when we're doing a simulation, if we have access to the whole state vector, that's great. We can compute exactly what the expectation value would be. But in the real lab, like you can't just reach in and grab the state vector, or at least if you can, like please let us know. So in the real world, what you would actually do is you would run the same circuit many times, like with a certain number of shots. And what you may want to do is say, okay, like if I do this, with 10,000 shots, what sort of distribution should I expect to see? And so if you're doing a classical simulation where you do have access to the state vector, you can also do something equivalent where you run the entire circuit once, and then you can take like 10,000 samples from it because you have the full probability distribution. And just as a reminder, we can get the probability distribution by squaring the absolute value of the amplitudes, assuming that psi is normalized, which I will assume for now because I hate normalizing things. So a common way we can just naively sample this probability distribution is to take a cumulative sum of all of these probabilities for each possible basis state, normalize the new vector, and then you just compute a random number between 0 and 1, find the two elements that it's between, and that's the measurement outcome. And so we can implement this. I've called it again naive sample. So this picks the first element of the cumulatively summed probability distribution, which is larger than the needle, and this corresponds to whatever bit string we would actually observe in a real experiment. And we can do this a number of shots times. So here, this is actually implemented by first computing the absolute square of all the amplitudes, okay? Then we compute the cumulative sum of those probabilities and normalize it. And then for the certain number of shots we have, we compute a random number between 0 and 1, the needle. We find the first probability in this cumulative sum that's above it. And whatever integer that is the basis state that we would expect to observe. And then we just return the number of shots. So this function, cumulative sum, just adds up all of the numbers to the left of it in the array. So here's a little example. It's called, another name for it is prefix sum or scan, because nothing in the world can ever have one name that people agree on. But Julia calls it this. And so if you apply this to this 5-element array, you can just see that, for example, like 4 plus 1 is 5. And then another 5 added is 10. Another 3 added to that is 13. And another 10 to that is 23. So some easy tests for whether a naive sampling function actually works are GHZ or cat states, which are just an even linear combination of all up or all down. So in this simple example here, we create just a really, really simple GHZ state, or GHZ, whatever you want to call it, for 5 qubits. And we compute the naive samples. And in this case, we should indeed either get 32 or 1. I forgot to subtract 1 there. Sorry about that. Which corresponds to all up or all down. So if I subtract 1, then it's all 5 ones. And if it's 0, then it's all zeros. Okay, great. Another option is to sample over a state vector which has equal probability amplitudes for all bit strings. Again, I came up with a little sort of a goofy one here. But you could try this even with something with complex phases. So this is a relatively naive way to do this sampling. And it's again sort of like the naive approach we showed earlier. It's actually totally fine to do this if the number of shots you have is small. Like if you need like 10 shots or fewer, for whatever reason, this or even more than that, this works really well. But if you need very large numbers of shots, as we'll see, this doesn't always work that well. And we can discuss why that is. But there are actually some better choices we can make that can allow us to sample from a state vector like this very efficiently. So the main one we're going to look at is called an alias table. So this is I guess like a pretty well established technique for doing what's called discrete categorical sampling, where you have effectively a list of discrete bins. So the shot outcomes, and you have a weighted probability distribution over those bins, and you want to sample from it effectively. So the nice thing about this is that it allows us to construct a lookup table in O(n) time once, and then we can do lookups from this table in O(1) time subsequently. So the difference from the naive sampling is that for the naive sample, we have to do an O(n) linear search every single time. So where the crossover between these two happens really depends on the prefactor, and that also is controlled by the shape of the probability distribution. But in general, for large numbers of shots, this alias table technique is a really effective way to generate large numbers of samples quickly. And there's lots of different implementations of this, but one that we do have in Julia has the really exciting name of aliastables.jl. Like they really went out there with this one. So we're going to use this to construct some categorical sampling. And this is also pretty simple. We just construct the weighted probability distribution here. So we just give the alias table a list of all the probabilities, and then the package builds the table for us, and then we can sample from it very efficiently for n shots. And here again, we just do some simple sanity checks to make sure that the output we get is reasonable. And so here, slightly down lower, I've done some chair marking where I look at a 14-qubit random state vector and I just take 20 shots. And perhaps unsurprisingly, the alias sample is about 5 times slower, although they're both microseconds, so it's not such a huge difference. But then a little bit lower down, we can see for 500 shots, even already only for 14 qubits, the alias tables perform substantially better. It's about 5 times faster. So it doesn't necessarily take that many shots for a technique like this to work pretty well. And I just mention it because this is the kind of thing also, like if you are having to compute 10,000 shots, it can be an easy win to use something like this for these kind of lookups. And you might also say, I feel like I keep banging this drum that, like I don't want to have to know about these stupid CS data structures like an alias table. Why does this matter to me? I hate my life. Why are you telling me about this? And it's fair that you may not know or want to know that much about it. But it's the kind of thing that at least if you've heard the words, you can say like, okay, if I really have to compute 20,000 shots per circuit, then I know a quick way I can do it without having to try and reinvent the wheel or waste a huge amount of time doing 20,000 ON operations. So I just mention it so that you kind of know what it is. But if you're not interested, you absolutely don't need to worry how this alias table is constructed or specifically how it works under the hood. Okay. So the last thing I wanted to talk about was doing density matrix-based simulation. So this allows us to simulate the effect of noise on a quantum circuit. Of course, we know that real quantum devices that are not fault tolerant are very vulnerable to noise. So being able to simulate the effect of noise is pretty important if we want to understand what the quantum device is doing, or in many cases more accurately, what it's not doing. So one option for doing noise simulation would be like sort of Monte Carlo-based noise simulation, where you run the state vector-based simulation as normal, and then you use some sort of Metropolis-Hastings procedure to project every time noise is applied onto the outcome of that noise. So we're not going to cover that today, but that's another option that you can also look at implementing if you're interested, especially if you're already familiar with Metropolis-Hastings sampling. In this case, though, we're going to look at a simulation that's based on the density matrix, which gives us full information about what's happening in the system. So, of course, we can form a density matrix for a pure state just by computing the outer product of the state vector. So in such a pure state, we just can always write the the density matrix like this. But once we have, so in the case of the quantum circuit, noise that's affecting the system, we may move out of the pure state scenario into something called a mixed state. So we probably don't have time to go through the entire basis of the difference between a pure and mixed state, but effectively for mixed states, we can no longer write the density matrix in a single utter product form like this. And so these states are often generated by noise acting on any quantum system or interactions with the environment for open quantum systems in general. And we can model such noise as sort of these maps called Kraus maps or Kraus noise. And we can also describe them as CP-TP operations. And every time I forget what what every single letter stands for, but it's complete positive trace preserving operations. Thank you. So the trace of the density matrix is always 1. And for a pure state, the trace of rho squared is 1, but for a mixed state, it's not. So you can quickly check, depending on the size of your matrix, I guess, if your density matrix is pure or mixed, based on whether the trace of its square is 1 or not. So in fact, also we can write the quantum gates we want to apply as these Kraus operators, but for noise, we have to write them in this way. We have some unitary map U, and we just update rho by doing a 3-part matrix multiplication. So we have U hat rho times U hat dagger. U hat is whatever gate or noise we want to apply. And then if we want to compute expectation values, again, we remember when we emerged dampened steaming into the world and we learned basic quantum mechanics, that for a density matrix, the expectation value of some observable O is just the trace of O times rho. And whoever came up with the idea, like possibly me, that operators are O and rho is the density matrix and they rhyme, has a lot to answer for. So the question here, I guess, is whether we can implement a lot of this without having to write a lot of new code. So can we repurpose a lot of the bit shifting and even naive stuff we did previously for state vectors? Normally when somebody asks a question like this, I feel like the answer is supposed to be no, but in this case, in fact, we can do a huge amount of work by just slightly repurposing a lot of the code we previously had. So one thing we can, again, do here is just write a naive gate applicator code that lets us apply some gate naively to rho, the same way we did previously for state vector. Now we do it for a density matrix. So this should probably look pretty familiar. The only thing that's like really different is at the bottom here. Instead of now we do the full gate times rho times the full gate's adjoint. And again, we can go through and construct all of this and just check something by hand. The other option, of course, is we can compute partial traces and just make sure that we get the correct state vector out at the end after constructing this and applying the gate. Okay. So the social insight we're going to use to apply all the code we previously had to this case is to remember that the density matrix representation of an n-qubit state is a 2 by n by 2 by n matrix. So one way we could work around this is by reshaping this effectively and treating it as a state vector on twice the number of qubits. So if we are just a little bit careful with arithmetic, we can actually simulate almost all of the density matrix formalism we need by slightly extending all the code we wrote previously and effectively just mirror imaging everything into the other half of the sort of like false qubits. And this isn't really a proper state vector. For example, like for one thing, it's not really normalized, but this allows us to save a lot of time not having to re-implement all the kernels we did previously. So if you go through and you just reshape like one of these matrices, in this case, this one I generated above, which in this case is an outer product of 2 state vectors, so I should be able to recover something relatively reasonable here. And I reshape it just as a vector. Then we can start applying gates to this thing as if it were a state vector, keeping in mind that we're not really enforcing like any normalization condition. Yes?
It's like I think I asked it before, but because we have it here as well, doesn't matter how like right now we're going from decimal to like how we do the and how will it affect.
So in this case, we're effectively relying on the fact that Julia is column major. So actually, this is another opportunity for me to draw something with the marker I already broke. So for the reduced density, this might also make this a little more obvious. row is equal to log here. We've got like
You want better markers?
no, this is fine. This is fine. I'm just like destroying them because I'm pressing too hard. I'm not going to draw the entire all the rows in row. Cool. Okay, so we have this matrix here that's like some reduced density matrix. And then if we just naively reshape this in Julia, it's gonna use the fact that this thing is column major. So I have colors. Oh. Okay. So when Julia actually indexes this, it goes down here. Okay, this marker sucks.
You can use this blue marker.
Whoa! Nice. That was a good toss. Oh yeah, this is way better. So it goes down like this, and then comes up back here, and then down like this, and then up and down. And then I kind of stretched this guy as I went. So from the point of view of this thing becoming like a fake state vector, so I'm gonna put it in quotes so that you know it's like really dubious. This thing would then be okay. So this would be like row 0, 0, and then row 1, 0, and then row 2, 0, row 3, 0, row 0, 1, blah 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 blah. Yeah. And I'm gonna write this nice. And then from this, you can even figure out like this thing is like, again, we're gonna pretend this is a pure state. That's 0. Is that 1? Or the 1 here is like kind of confused with indices. So this is on all zeros, this is like on 0, 0, 1. This would be like, yeah, like size 0, size 2. So you have to actually, to get the full list of qubit states, you have to expand out this integer. But since I didn't really give myself a lot of room, I'm not going to do that. Hopefully it's relatively clear. So then you can also like effectively apply that to these indices here and use that to plug back into the bit shifting you did previously. So that's where this claim, I guess, comes from, that this thing, you can sort of look at it as if it were a state vector on twice as many qubits as it really is. And then you just apply every single operation twice. Once the regular way, and then once shifted into like the mirror dimension with plus the correct number of qubits. Okay. So it's also worked out in the notebook a little bit how this actually happens. You can go through the Einstein summation if you're interested, but effectively, if we treat this thing as like a 2 to the n vector, we've doubled the number of qubits. Okay. So this means, for example, like if we can do a state vector simulation of 32 qubits, the density matrix simulation, we can only do 16. But in a way that's okay because with the noise we have twice the information, we're not throwing anything away. If you do this with the Metropolis Hastings sampling, you can go to a larger number of qubits, but you don't have full information about where all of the, I guess, the information in the system is gone. And there's a little bit more of a worked example here. I'm trying to like get through enough of this that people can actually get to the exercise. So if you're confused by it, definitely come up and ask later. We can effectively treat all the bottom half of this.
Excuse me.
Yeah.
You just said something about if you could do 32 qubits before you could do 16. Now, can you explain that again?
Yeah, so effectively what we're doing is we're treating this row, which is 2 to the n by 2 to the n. So
You'd be able to do a matrix that's a square root of that size, right? So the vector has, if your state is size 2 to the n,
yeah,
your density matrix vector is now size 2 to the 2n,
yes.
or 2 to the Yeah, 2 to the 2n, right?
Yeah,
Because
yeah,
it's squared.
exactly.
Okay.
Yeah, so you can do half the number of qubits if you're using the density matrix. So it's hard. So when you're speaking and also the exponents too, be like, where are all the twos? So yes, this is length 2 to the 2n. It's kind of a pain. And effectively, you can treat like the row indices here as the main qubits, and then the column indices here as like the sort of shadow extra double qubits. So when you apply the gate, and I have a little bit, I guess, also showing how you can construct the expectation value in a naive way, which you can look at if you're super interested. We can then effectively simulate this by just applying, like whatever u it is to the initial qubits, so like 0 to n, and then the u adjoint to the I don't know why I keep calling them shadow qubits, but I guess it sounds cool, to the n+1 to 2n qubits. So there's like a little bit of an exercise here where you can try and extend the bit shifting stuff we did previously and use that to treat this sort of false state vector here without actually having to write any new kernels. So you can apply Kraus noise to some reduced density, or not reduced, I don't know why I keep saying it's reduced. You can apply Kraus noise to this density matrix without having to write any new functions, as long as you're a little bit careful about accounting for where the specific operator is applied in the list of qubits that are real and fake. So I'll leave that to people as an exercise to try. And here, for example, is a specific case of like this kind of Kraus noise. This is a bit flip operator where you have a flip that occurs with probability p. So the way you can write the full form of this operand is this bad boy right here. So it's an unfortunate convention that everyone calls the probability p, and also the density matrix operator is rho, which look extremely similar. I don't know why people stick with this convention, but they do. But I guess like the final exercise for today, given we have about 15 minutes left, or for however long you want to go, is to try and extend the code we wrote previously to work for this density matrix in the state vector format. And then if you really want to go crazy with it, you can try applying Kraus noise on multiple qubits. And I think that's basically everything I had that will fit today, but there's a little bit more here if you're interested in looking at it. And with that, yeah, thanks. You can work on the final exercise or do something else, or yeah, questions.